Hello everybody. Next, let us look at how to write the velocity kinematics for serial manipulators. Here, for the first, we are going to take the Cartesian manipulator. We will try to take for each and every case, for Cartesian, for spherical, for cylindrical, for scara, articulated. These are the five structures we have studied. So out of that, the first one is the Cartesian manipulator. I have taken the same image that I have used for deriving the forward kinematics and the inverse kinematics, because there is no point in drawing a new structure. And I have also added the link parameter table because the same process is repeated for deriving the velocity kinematics. Now, as you can see here, we have used the DH method to come up with the frame and then come up with the link parameter table. It is the same that we have been doing in module 4 for finding out the transformation matrix. If you remember, we had done this exercise, and then using the AI matrix we found out what was A1, A2, A3, and then finally we found out what is the total transformation matrix. We are interested here because the rotation matrix is the 3 by 3 matrix that we have you know from this transformation matrix. So the same procedure is used. What we are interested in is A1, A2, A3 using this equation. So the same set of equation and A1, A2, A3 value can be obtained just as we have seen in the case of forward transformation. So I will quickly write what is the A1, A2 and A3 value. So here is the A1, A2, A3. So remember, we have used the DH convention for arriving up till this much point. This we have already done previously in the fourth module. So once we have got A1, A2, A3 using the equation of DH, next what we are going to do is we are going to define what is the velocity kinematic equation. For basically the velocity kinematic equation, let me write it here. The velocity kinematic equation is basically written in the form that you are having 0 Vn 0 omega n, that is equal to J matrix, and then you are having here we are having 3, so I will just write D1, D2 and D3. So the differentiation of that is going to be the equation for us. So I will just write the dot, I will put the dot here. So D1 dot, D2 dot, D3 dot. So this is a 3 by 1 matrix. This is going to be a 6 by 1 matrix. 6 by 1 matrix. And so this will be a 6 by 3 matrix. So how to come up with this 6 by 3 matrix? That is what the task we have for us. So let me write where J, which is a 6 by 3 matrix, will have a structure which comprises of for 3 joints. So I'll have of joint 1, joint 2, joint 3. So I will just put a line that separates the columns for the 3 joints, and then here I will have to write for joint 1 what is the joint 1. I will have to write I is equal to 1. The second joint 2, I have to write I is equal to 2, and for joint 3 similarly I have to write for I is equal to 3. Now if you look at the Cartesian structure here, what we find is that all the 3 are prismatic joints, and for prismatic joint this is the simple formula. If you remember, I had already talked about this in the previous video. For prismatic, writing the column we use these two. So the same one I will write. Remember here I is the number of the current joint. Okay. So based on that, I can very clearly say that here it will be, let me use a different ink. Here it will be R 0, I is 1 here, so I minus 1, which is 1 minus 1, is going to be 0, and then 0 0 1. Similarly, the bottom part, the bottom three values are going to be all zeros, because we have already seen that in prismatic it is 0. Similarly, for the second joint it will be 0 R, I is 2, so 2 minus 1 is 1, 0 0 1. The bottom part is going to be 0 0 0. Similarly, we are having 0 R2 and 0 0 1, and we'll be having 0 0 0. So just for, because I'm doing it for the first time, so I will write here 0 R0 is rotation matrix, is the rotation matrix of the transformation matrix 0 T0. Similarly, 0 R1 is the rotation matrix, of 0 T1. Similarly, 0 R2 is the rotation matrix of 0 T2. Now, what is basically 0 T0? 0 T0 means trying to shift a frame from 0 to 0 itself. So actually there is no shifting here. So if you remember, we used to generally write in that case identity matrix 0, then all zeros, 3 zeros followed by a 1. That was for this case. For this one, 0 T1, it will be simply a 0, not 0, a1, sorry. It used to be a1, and that means I will correct it. 0 T1 is just the first one, so it is going to be just a1. This is going to be a1, sorry. So this is going to be a1. Similarly, 0 T2 will be a1 into a2. Based on that, we will be able to write the 3 matrix, and then we'll be able to write the answers for it. So based on that, I will be able to complete this if I am able to take a1 a2. So I will again borrow a1 a2 from here. So a1 a2 a3, if I take it from here and put it here again, then I can find out these rotation matrix. So first I will write 0 R0, as I told, it's straight away going to be the identity matrix. So 0 R0, therefore 0 R0 is just the identity matrix, because as I told you, for moving from 0th frame to 0th frame, you don't require any movement or any rotation. So 0 R0 will be this one. Now for finding 0 R1, as it's already written here, we are only going to take, for 0 R1, we are only going to take 0 T1, which is A1. From A1 I will write the three values of the rotation matrix. So the 3 by 3 matrix of the rotation. So I have to take these values. So it is 1, 0, 0, 0, 0, 1. So I will straight away write that 1, 0, 0, 0, 0, 1, 0, minus 1, 0. Now the next one is uh, 0t2. From 0t2 we will be taking 0r2. Now there is no need to multiply the 4 by 4 matrix. You can straight away multiply the 3 by 3 matrix of 0r1 and 0r1r2 for finding out the answer. But since it's a 4 by 4, I will just do it here once. So, and since 0t2 is a1 into a2, I will multiply, therefore 0t2, I will try to multiply and get the answer. So if I multiply this one, I will get the answer as this, from which therefore I will get the 0r2 by just taking the 3 by 3 matrix of the rotation part here. Therefore the 0r2 is going to be, from this one itself, it's going to be 0, 0, minus 1 and 0, 1, 0, similarly 1, 0, 0. So now I have to multiply with 0r0, 0, 0, 1. So I will straight away write, therefore I have to multiply each one, isn't it? Therefore 0r0 multiplied with 0, 0, 1. So if I'm going to multiply this with this particular matrix 0, 0, 1, if I'm going to multiply with this one, as I can see, it is directly going to pick only the last column because it is 0, 0, 1. So the last column will be picked. So I will use that to finally write the answer as 0, 0, 1 itself. So it is going to be 0, 0, 1. And the next one is 0r1, isn't it? The next column we are having 0r1 multiplied with 0, 0, 1. So 0r1 multiplied with 0, 0, 1, it means that I am going to straight away take the third column from here. From 0r1 I am going to take the third column, which is going to be 0, 1, 0. And from the last one, and 0r2 multiplied with 0, 0, 1 is going to take the last column from this one, which is going to be minus 1, 0, 0. Therefore the Jacobian matrix for, so let me write it in a different color. Therefore the Jacobian matrix, straight away taking from this above equation that we have written. So if you look here, so I'll substitute these values directly, which are these three values. So it will be 0, 0, 1. As we have already seen that the last three values are all zeros above. Similarly, I am having 0, 1, 0 from this one, and then followed by 3 zeros because it's a prismatic joint. Similarly, the last one will be for 0r2, so it is going to be minus 1, 0, 0, followed by the 3 zeros. And that's how the Jacobian matrix will look. So based on that, I can find out the velocity kinematics. Therefore the velocity kinematics is x dot, y dot, z dot omega x, omega y, omega z, it's going to be because of the multiplication with j, which is this same matrix. I will straight away take from here, and then the three joints, as we already have seen here, the three joints are having a joint variable of d1, d2, d3. So that same joint variable I'm going to put here, but as differentiated component. So it will be d1 dot, d2 dot, d3 dot, and that's the matrix, and from this we can find out what is the velocity. So I have directly written here the velocity. If you remember, we have written it in a different form, so let me write it in this particular values. I will write it in a different form that I have later written it as. It's basically the velocity of v in x direction, the nth frame. Similarly, the velocity in y direction of the nth frame, the velocity with respect to 0 of z direction of the nth frame, and then we are straight away having 0 omega x, 0 omega y, and 0 omega z. So this is how we write. So based on that, if I am going to do the multiplication, I will get the answers. Let me write the answers straight away here. So therefore, from here I can directly write the different values of therefore. So what is Vxn? Vxn is going to be the multiplication. So if I multiply it here, it will be dot d1, dot d2, dot d3. So I will have to multiply each and every one. So therefore Vx0, Vx of n will be equal to minus d3 dot. Similarly, the velocity in y direction will be given by, if I multiply, it will be dot d2. Similarly, I will get 0 vz, that is velocity in the z direction, it will be dot d1. And that is the answer of the velocity. So what does it say? It says the velocity of the end effector in the x direction. It's very important to understand this. Okay, the velocity of the end effector in x direction depends on the negative velocity of the d3. So what is d3? So if you remember here, d3 is basically this axis. So this is the d3 is the x-axis of the base frame, isn't it? So d3 motion is in minus of x. It's in minus x0 direction. So that is why the velocity of d3 will determine the velocity of the in the x direction. Similarly here, according to the base frame, z0 is in this direction. The velocity of d1 will decide what is going to be the z direction velocity of the end effector. Similarly, the y-axis will come in this direction, which is basically because of d3. So not d3, d2. So the velocity of d2 will determine what is going to be the velocity of the end effector in y direction, and that is what we have actually got as the answer here. So we directly get the velocity kinematics of the end effector. Thank you.